Mariana Trench. Nearly 7 miles beneath the ocean surface, it's the deepest place on Earth.
Nobody thought the ocean was this deep. So all of a sudden we've got scientists saying, why is that?
For decades, it remained one of the planet's last true mysteries, hidden under crushing pressure and absolute darkness. Then, artificial intelligence did something remarkable.
Hey, what do we have here?
It mapped the entire floor in unprecedented detail, and what it found has left scientists scratching their heads.
People were probably astounded by what they were seeing because clearly the ocean floor had enormous changes in relief, was very mountainous in some places, had great deeps in other places.
Strange formations that shouldn't exist, patterns no one can fully explain.
Really hard to know what these marks are.
Are they even underwater, or are they just reflections off the top of the surface of the water?
It's almost like something is digging into the sea bottom.
And geological features that challenge everything we thought we knew about the deep ocean. The Mariana Trench, Earth's final frontier. Located in the western Pacific Ocean, east of the Philippines, the Mariana Trench stretches for over 1,500 miles. At its deepest point, called Challenger Deep, the ocean floor sits nearly 36,000 feet below the surface. To put that in perspective, if you dropped Mount Everest into the trench, its peak would still be more than a mile underwater. Only 3 people have ever descended to the bottom. Jacques Piccard and Don Walsh made the first trip in 1960, spending barely 20 minutes down there before heading back up. Film director James Cameron went solo in 2012. That's it. 3 humans in over 60 years. More people have walked on the moon than have visited the deepest part of our own ocean. The trench formed where the Pacific Plate slides beneath the smaller Mariana Plate, a process called subduction. As one massive chunk of Earth's crust dives under another, it creates this enormous underwater canyon. The geology down there should follow predictable patterns based on this process. Scientists thought they understood the basic structure pretty well. Mapping it in detail, though, that was a different story entirely. Early exploration attempts relied on simple depth measurements and occasional manned submersibles that could only survey tiny areas. It was like trying to map an entire continent by looking at a few parking lots. The technology just wasn't there to see the full picture. Until recently, most of the trench remained as mysterious as it was a century ago. Why mapping the ocean floor is nearly impossible. The pressure alone is mind-boggling. At the bottom of the Mariana Trench, every square inch experiences over 16,000 pounds of force. That's like having 50 jumbo jets stacked on top of your thumb. Most materials simply crumble. Even specialized equipment built from titanium and ceramic can only last so long before the ocean wins. Then there's the complete absence of light. Sunlight penetrates maybe 650 feet down on a good day. Below that, it's darker than any night you've ever experienced. Cameras are useless without powerful lights, which need massive amounts of energy. That means bigger batteries, heavier equipment, and more things that can fail under pressure. Traditional sonar mapping helped create rough outlines of the ocean floor, but the resolution was terrible. You could identify major features like mountains or valleys, but the details remained fuzzy. It's the difference between seeing a blob on a map and actually making out individual buildings and streets. For precise mapping, you need to get close to the seafloor with advanced sensors, but keeping equipment operational at those depths for extended periods across hundreds of miles, nearly impossible with conventional methods. Here's the strange part. We have more detailed maps of Mars than we do of our own ocean floor. Satellites and rovers have photographed and analyzed Martian terrain for decades, but water blocks satellite signals, and the ocean is vast beyond comprehension. So the floor of the Mariana Trench remained largely unknown, hiding whatever secrets it held in the crushing dark. Enter AI, the game changer. Machine learning changed everything. Instead of relying solely on new hardware to explore every inch of the trench, researchers realized they could use artificial intelligence to extract far more information from existing data. Decades of sonar readings, depth measurements, and scattered high-resolution surveys had been collected. The problem wasn't lack of data anymore. It was making sense of it all. AI systems excel at finding patterns humans miss. Feed them enough information, and they can interpolate what's between the data points with surprising accuracy. Scientists developed neural networks specifically trained on seafloor topography. These systems learned what underwater mountains look like, how trenches form, what patterns appear around volcanic activity. Then they applied that knowledge to the fragmentary data from the Mariana Trench. The breakthrough came from combining multiple data sources. Satellite measurements of the ocean surface can detect tiny variations in water height caused by gravitational pull from underwater features. Sonar sweeps from research vessels provided depth profiles along certain routes. Autonomous underwater vehicles captured high-resolution scans of small areas. Separately, these datasets left huge gaps. But AI could weave them together, filling in the blanks based on what geological features should exist given the surrounding context. Advanced algorithms processed millions of data points, identifying relationships and structures that would take human researchers lifetimes to spot. The AI didn't just create a map. It revealed the trench in detail never before possible, showing features as small as a few meters across the entire sprawling formation. When scientists examined the results, they expected to see confirmation of existing theories about trench geology. Instead, they found things that made no sense, what the AI actually found. The complete map revealed the Mariana Trench is far more complex than anyone imagined. The main trench wasn't just a simple V-shaped cut in the seafloor. Instead, it showed multiple parallel ridges, smaller sub-trenches branching off at odd angles, and variations in depth that followed no predictable pattern. Most surprising were the numerous flat-topped seamounts rising from the trench floor. These underwater mountains shouldn't exist down there. Seamounts typically form from volcanic activity, and while the Mariana region has volcanism, finding so many within the trench itself was unexpected. Some rose thousands of feet from the floor, but remained well below the ocean surface, their flat tops suggesting they were once islands that sank or eroded away. The AI also identified what appeared to be massive boulders scattered across certain sections of the trench floor. We're not talking about rocks you could pick up. These were structures the size of buildings, sitting in places they had no obvious reason to be. Where did they come from? How did they get there? The pressure and geology of the trench should have crushed or buried such formations long ago. Strange linear features appeared in the mapping data too. Long straight ridges running for miles, parallel to each other in some areas. Natural geological processes rarely create such regular patterns. Rivers and erosion make curved, branching shapes. Tectonic activity produces cracks and faults, but these look different. Too organized, too deliberate, almost. Perhaps most perplexing were the circular depressions identified at various points along the trench. Perfect circles, or near enough, punched into the seafloor. Some measured over a mile across. These weren't volcanic calderas or impact craters. Their edges were too smooth, too uniform. Scientists examining the AI-generated maps couldn't immediately explain what natural process would create such features. The bizarre geology that shouldn't be there. Traditional understanding of trench formation says they should be relatively simple structures. One plate slides under another, creating a deep, curved depression. The seafloor material gets dragged down into Earth's mantle, melts, and eventually causes volcanic activity further inland. It's a well-understood cycle. But the Mariana Trench, as revealed by AI mapping, doesn't quite follow the script. The multiple parallel ridges running along the trench are particularly odd. Current tectonic theory doesn't predict these secondary structures. They suggest something more complicated is happening as the plates interact. Maybe the subducting Pacific plate isn't sliding smoothly. Perhaps it's fracturing in unexpected ways, creating these additional features. But that raises questions about stress distribution and material strength that challenge existing models. Those flat-topped seamounts present another puzzle. If they're old volcanic islands that sank, why are so many clustered in this specific area? The region's volcanic arc lies well to the west, where you'd expect such features. Finding them within the trench means either they formed there, which seems unlikely given the geological processes at work, or they moved there somehow. Tectonic transport could explain it, but the positions don't quite match predicted patterns of plate movement. Some of the detected formations resemble mud volcanoes, which form when pressurized sediment and fluids force their way up through the sea floor. These have been found in other deep ocean areas, but the sheer number in the Mariana Trench and their unusual distribution suggest mud volcanism might be far more active there than anywhere else on Earth. What's driving all that subsurface pressure and fluid movement? The answer could reveal new details about how water and minerals circulate through Earth's crust. The massive boulder-like structures remain the biggest geological head-scratcher. You don't get building-sized rocks sitting on the deep ocean floor without some dramatic process putting them there. Landslides from the trench walls? Possible, but many of these rocks sit too far from any slope. Volcanic ejecta? That would require truly massive eruptions. Or could they be remnants of the subducting plate itself, somehow fractured and left behind? No existing theory fully accounts for what the mapping revealed. Strange patterns and unanswered questions. The AI didn't just map the trench. It identified patterns in the data that human researchers would have missed. One of the most intriguing involves the spacing of certain features. Smaller seamounts and ridges appear at remarkably regular intervals in some sections, almost like they were placed on a grid. This kind of regularity screams for an explanation, but geology doesn't usually work with such precision. Natural processes can create repeating patterns. Sand dunes, for instance, form at regular intervals based on wind patterns and sand availability. But those are surface features shaped by fluid dynamics. The deep ocean floor doesn't have comparable forces acting on it, at least not that we know of. So what's creating this regularity in the trench? Another pattern involves chemical composition. While the AI mapping focused on physical topography, follow-up surveys of certain areas revealed unusual mineral distributions. Specific types of rock and sediment appeared in clusters that didn't match the expected results of normal erosion and deposition. It's like finding patches of desert sand scattered randomly across a forest floor. Something transported or formed these materials in ways that standard geological models don't predict. Temperature variations detected by deep-sea probes show similarly weird patterns. Hydrothermal activity should create hotspots at predictable locations based on tectonic forces and magma presence. But some of the warmest areas in the trench appear far from any obvious volcanic features. Either there are magma chambers we don't know about, or heat is being transported through the seafloor in unexpected ways. Both possibilities have major implications for understanding Earth's interior. The AI also detected what might be acoustic anomalies. Sonar doesn't just bounce off the seafloor, it penetrates slightly, revealing information about sediment layers and subsurface structures. In certain parts of the trench, the returning signals showed complex layering that suggests buried features. Old lava flows, ancient reefs from when the area was shallower, sediment deposits from long-ago tsunamis. Without drilling and direct sampling, which is incredibly difficult at these depths, scientists can only speculate. Life in the absolute darkness. The detailed mapping revealed far more hydrothermal vents than previously known. These underwater geysers spew superheated mineral-rich water from beneath the seafloor, creating oases of life in the otherwise barren deep. Around each vent, entire ecosystems thrive despite the crushing pressure and absence of sunlight. Strange creatures cluster around these vents. Giant tube worms, some over 6 feet long, anchor to rocks and absorb chemicals from the vent water through specialized bacteria living in their tissues. Eyeless shrimp swarm in the plumes, their bodies adapted to sense heat and chemicals instead of relying on sight. Crabs, fish, and species that don't even have common names yet all make their living around these deep-sea hot springs. What makes these ecosystems remarkable is that they don't depend on the sun. Every other habitat on Earth ultimately relies on photosynthesis. Plants capture sunlight, something eats the plants, something else eats that, and so on. But vent ecosystems run on chemosynthesis. Bacteria harvest energy from chemical reactions between vent minerals and seawater, forming the base of a food chain that exists in total darkness. The AI mapping identified potential vent sites by looking for the characteristic topography and mineral deposits they create. Many of these predicted locations haven't been visited yet. When researchers finally send cameras and sampling equipment, they might discover entirely new species. The life forms down there are so alien, so adapted to extreme conditions, that they help scientists understand what life might look like on other worlds. Moons like Europa and Enceladus have subsurface oceans. If life exists there, it might resemble what we find in the Mariana Trench. Some of the most bizarre recent discoveries came from baited cameras dropped into the deepest areas. Snailfish, translucent and gelatinous, swim casually at depths that would implode most creatures. Amphipods the size of dinner plates scavenge whatever organic material drifts down from above. And then there are things researchers can't even classify yet. Strange swimming forms captured on video, living at pressures no complex organism should survive. The more we look, the weirder it gets. The detailed floor map also revealed sediment patterns that suggest biological activity. Small mounds and depressions, the kind that organisms create as they burrow and feed. Life isn't just clinging to vent areas, it's spread across the trench floor, sparse but present, surviving on the thin rain of organic material that drifts down from the sunlit waters miles above. These creatures live life in slow motion, their metabolism throttled by the cold and limited food. But they're there, proof that life finds a way even in Earth's most hostile environment. What this means for science. The unexpected complexity revealed by AI mapping forces scientists to rethink plate tectonics. The models that describe how Earth's crust moves and interacts worked fine when we only had rough outlines of features like the Mariana Trench. But now we can see details those models don't predict. Either the models need significant adjustments or there are processes at work we don't understand yet. Understanding what's happening at the trench has implications for earthquake prediction. Subduction zones generate the planet's most powerful earthquakes. The 2011 Tohoku earthquake that devastated Japan and triggered the Fukushima disaster happened at a subduction zone. The more we understand about how these areas behave, the better chance we have of predicting when and where the next big one will strike. The strange geology in the Mariana Trench might reveal warning signs scientists haven't known to look for. Climate science benefits too. The ocean floor isn't static. It interacts with seawater, absorbing and releasing chemicals that affect ocean chemistry and, eventually, atmospheric composition. Carbon dioxide dissolves in seawater, and some of it ends up locked in seafloor minerals through various chemical reactions. How much carbon the deep ocean can store, and for how long, plays a role in climate models. The detailed mapping helps scientists understand these processes better, revealing where and how ocean crust interactions occur. Then there's the astrobiology angle. If we want to find life on other worlds, we need to understand life in extreme environments on our own planet first. The creatures thriving in the Mariana Trench prove that life doesn't need sunlight, moderate temperatures, or low pressure. It just needs energy, raw materials, and liquid water. That broadens the range of potentially habitable environments throughout the solar system and beyond. The trench isn't just about Earth, it's a window into what's possible for life anywhere. The mapping might also reveal resources. The deep ocean floor contains valuable minerals, including rare earth elements crucial for modern electronics. Manganese nodules, metal-rich lumps that form on the seafloor, sit scattered across abyssal plains and trench areas. As land-based resources become harder to access, mining companies are eyeing the deep ocean. Whether that's a good idea environmentally is a whole other debate, but accurate mapping is essential if it's going to happen. We need to know what's down there before anyone starts digging it up. The future of AI in ocean exploration. AI is just getting started in ocean science. The Mariana Trench mapping demonstrated what's possible, but the technology continues improving. Next-generation algorithms can process even more data types simultaneously, creating maps that show not just topography but also temperature, chemistry, biology, and geology all at once. Imagine a visualization where you can see the physical structure of the seafloor, the location of every vent and organism cluster, the flow of deep currents, and the distribution of minerals, all in one comprehensive model. Upcoming missions will combine AI with autonomous vehicles that can explore for months without human intervention. These robots will swim through the deepest waters, collecting data and making decisions about where to go next based on what they find. If they spot something interesting, they'll investigate further without waiting for instructions from the surface. It's exploration at a pace and scale that would be impossible with human-controlled equipment. Machine learning will also help predict where we should look for specific features. Want to find new hydrothermal vents? Train an AI on known vent locations and the geological characteristics surrounding them, then have it analyze maps of unexplored areas. It'll point you to the spots most likely to have active vents, saving time and resources. The same approach works for finding shipwrecks, undersea volcanoes, or potential mineral deposits. Other trenches in deep ocean areas will get the same treatment. The Mariana is just one of several major trenches on Earth. The Tonga Trench, the Philippine Trench, the Peruchil Trench, each has its own unique characteristics and mysteries. AI mapping will reveal them all, piece by piece, until the ocean floor is as well known as the continents. We're still years away from that goal, but the progress is accelerating. The same technology might even extend beyond Earth. If we ever send submarines to explore the oceans of Europa or Enceladus, they'll likely use AI systems descended from the ones mapping our own seafloor. The challenges are similar: vast areas, limited access, hostile environments. What we learn exploring the Mariana Trench today could guide the design of probes exploring alien oceans decades from now. The AI revolution in ocean science is happening right now. Every few months brings new capabilities, better algorithms, and deeper insights into the last unexplored frontier on Earth. The mysteries are still there, but we finally have the tools to solve them. The Mariana Trench was just the beginning. The deep ocean is giving up its secrets, one AI-generated map at a time. And what we're finding down there is stranger than anyone imagined.